All right, hello everyone. Welcome to week 6 of our Biochem weekly reviews, and this is going to be one of the more fun weeks because we get to actually do some real biochem and not a ton of memorization or general chemistry stuff. So this is the week that I think really separates biochem as a subject. So we're just going to go ahead and jump right in because it's a pretty big week. So the first two questions are something we talked about very briefly last week, but since this week is all about enzymes, I wanted to bring them up one more time to review. And it's about the classes of enzymes. So there are 6 classes of enzymes that catalyze reactions. For both sections of biochem, you need to know all 6 of these classes. I've listed 4 here as the multiple choice options, but we'll talk about them in a little bit. The important part is that in this case, they're cleaving disulfide bonds. So a disulfide bond is the bond between 2 sulfurs in usually cysteine, be something like that, and then the rest of the amino acid. So this reaction, a lot of people would assume it would be a ligase or a lyase acting in reverse that's cleaving this reaction. However, this is one of the stranger ones. The way that we break these disulfide bonds is by adding reducing agents. Okay, and we can remember that from our previous few weeks where we've been talking about protein sequencing, the way that we break these disulfide bonds, reducing agents. That indicates to us that this actually has to be a redox reaction. And since it's a redox reaction, an oxidoreductase is going to catalyze the reaction in the forward and the reverse direction. Okay. What kind of enzyme would form a peptide bond? Okay. So this question actually has 2 possible answers depending on whether you're talking about chemically or biologically. So chemically, a peptide bond, if we remember, is the bond made between the C terminus of one amino acid and the N terminus of the other. And then the rest of the amino acid. This nitrogen attacks at this position. What ends up happening is this OH is dropped, and as is one of these hydrogens. So as a result, H2O is released. So that mechanism indicates that it's a hydrolase. However, in our body, that's not the exact mechanism that happens. Because it's done in ribosomes, the ribosomes need a little bit of help, and so they actually have an ATP-catalyzed reaction. And as we'll see in this figure down here, when you have an ATP-catalyzed reaction, it tends to be a ligase, all right, especially when you're combining 2. So in this diagram we see here, it's protein A, or structure A, I should say, is excuse me, and structure B are coming together with some, and this XTP is just ATP, GTP, UTP, or CTP, and bringing the 2 of them together. So this is A and B, and it's using ATP to do so. And so that is a ligase. And that's actually what we have in our body forming these peptide bonds and forming these proteins. So the answer to this question would actually be either of these. However, based on just the mechanism, I'm going to go with the hydrolase. Just quickly to review the classes of enzymes before we jump into the actual math. Oxidoreductases, as discussed, will transfer electrons. Transferases transfer constituents, so a lot of the examples, an aminotransferase transfers an amino group, a phosphotransferase transfers a phosphate group, things like that. A hydrolase will either cleave or synthesize a structure using water, so either water will be formed or water will be absorbed in that structure to do so. Lyases bring structures together without the use of energy. So A and B, those 2 are combined into AB. Isomerases move a substituent around on the same structure. And ligases, as discussed, are the same as lyases. They synthesize a new material, but they use energy to do so, or I should say an external energy source to do so. Okay, so hydrolases can break and form bonds, exactly. So if we notice, these are all double arrow reactions. And as I mentioned up here, with the peptide bond, you could speed that reaction up with hydrolase. It's very rare, but you could. When we look at DNA, in DNA you have DNA ligase. Do you remember what DNA ligase does? One of the weird ones, I know, but it connects two strands of DNA together into a double-stranded thing. And so what we see is DNA ligase, sorry, I'm trying to, okay, there we go. I wasn't sure why I wasn't scrolling down. Puts the two together, but they can also be used the other way, okay? It's not as common and it's not as sped up because, but when we think about the active energy hill, what an enzyme does is it lowers the activation energy. How? It stabilizes this transition state. The transition state is going to be the same in the forward and in the reverse reaction. However, simply because this initial energy is here and this final energy is here, we know what's going to happen more often than not. It's just technically possible for the reverse reaction to occur. Okay, really good question. Okay, all right, so now we get into the math. So in the above reaction mechanism, why is there no K-2? So this is one of the questions that a lot of students ask a lot of the time. And this kind of comes back to this idea right here as well. The reason there's no K-2 is kind of based on this concept. Because the formation of, or I should say the reaction of ES to enzyme plus product is so favorable, your K-2 is next to negligible. It is there and it does exist, but it's minuscule. And so we ignore it. So in some of your sections, I believe your professors may be calling K2 about equal to Kcat, where Kcat is the turnover rate, or like how quickly product is formed. They say it's about equal to Kcat. For the purposes of this class, it's equal to Kcat. The reason that it's not quite equal to Kcat is because K-2 does exist, okay? But because this reaction is so favorable, K2 is going to predominate this part of the reaction. Like this half is primarily driven by K2, and K-2 is pretty much negligible, okay? All right. Rapid equilibrium and steady state equilibrium. So these are some of the more confusing topics within this unit to a lot of students, and for good reason, to be honest. This is something that I also struggle with quite a lot. So they're based on two assumptions. First assumption is K-1 is significantly greater than K2. And when we say significantly greater, we mean by orders of magnitude, okay? So if I were to write about ES, and I were to say ES, I'm sorry, I'm just going to do that so we have some room to work. ES has two choices. It can either do the K2 reaction plus E, or ES do the K-1 reaction. And I'm not drawing double arrows since I'm only talking about this with respect to ES, but those are obviously still there. So since this enzyme substrate complex has both of these choices, rapid and steady state equilibrium rely on the difference between these two choices. And let me fill in K2 because I left that out. So when K-1 is significantly greater than K2, this reaction is the major reaction that happens. In other words, the breakdown to form product is slower than the breakdown of the enzyme substrate complex. Okay? So, and I don't like the term breakdown in this because the breakdown to form product, the reaction to form product is the way that I think about it, is slower than the breakdown of the enzyme substrate complex. Okay? So let's think about what that means. And I want to go ahead and do here. The reaction and the reaction. I think that's a little bit clearer. So when I have my enzyme substrate complex, it has those two choices. If K-1 is significantly greater than K2, then the first half of my reaction now, so the part that I'm highlighting in green here, is going to happen very, very quickly. And then every so often, relative to this reaction. It's still fairly fast in terms of like number of molecules being made. But so the green part is going to reach equilibrium very quickly. The yellow part every so often is going to make some product, and that's going to slightly shift the equilibrium, but it's going to get there really quickly again. And then more of the yellow reaction is going to happen, which is going to make the green recalibrate and so on. And that's why it's called a rapid equilibrium, because it reaches equilibrium rapidly and it changes somewhat rapidly. Okay? So, right. So the assumption that rapid equilibrium relies on, I kind of gave away. The breakdown to form product is slower than the breakdown of the enzyme substrate complex. That's correct. That relies on the assumption that K-1 is significantly greater than K2. So let's write the expression for the enzyme substrate complexes like capital K. Like, what is it going to do? So if we all remember from Gen Chem 1, or Gen Chem 2, I should say, K in general is equal to K-1 over K1. Okay? In other words, it's equal to the rate of the product, and I'm putting product in quotes here because it's not quite the product, breakdown over reactant breakdown. Okay? So when we say product here, we mean product of the equilibrium. We mean enzyme substrate complex. Okay? So the K of the enzyme substrate complex is equal to, on the top, the things that destroy or break down the enzyme substrate complex. Well, that's K-1 and K2. And on the bottom is K1, so just everything that forms it. Okay? Well, we said that K2 is pretty small relative to K-1. Oh, and I'm sorry, that should be a plus in between them. And so because K2 is next to negligible relative to K-1, simply because it's orders of magnitude smaller, K-1 is really the only thing we care about. And so for rapid equilibrium, the equilibrium expression that we use is Ks, and it's Ks is equal to K-1 over K1. Okay? Steady state, on the other hand, and I'd like to talk about that one just kind of from scratch again. Steady state does not have this assumption. This does not hold valid. So with steady state equilibrium, K-1 and K2 are close to each other. And I say roughly equal, I'm referring to orders of magnitude. So whereas K-1 in rapid could be like 10 to the third or 10 to the fourth bigger than K2, in this case, they're about the same order of magnitude, maybe one more or less than each other. So in this case, what's happening? The enzyme substrate complex can now break down or create two different products without without significantly favoring one or the other. And so because of that, as soon as the enzyme substrate complex is formed, it's going to go to either of them. Okay? And in fact, it's going to, what that results in is it results in a rate of synthesis about equal to the rate of consumption. In other words, as much enzyme substrate complex as you get coming from the forward reaction of K1, you get about the same product coming out of it. And so because of that, the concentration of enzyme substrate complex is about constant. Okay? And I know that's kind of unintuitive. But the reason that it's about constant is because it's being formed by the K1 reaction at the same time as the K2 reaction is able to consume it. Okay? Does that make sense? Okay. Yes, okay, awesome. So because of that, its equilibrium expression here, and that's called Km, is K1 plus K2 over K1. Okay, so answering that question of number 5, under which equilibrium does Km equal Ks? Under steady state. Oh, that's not quite right, I apologize. Under rapid equilibrium. Sorry, I mistakenly misread that question. So, and the reason there is because Km is this, but under rapid equilibrium, K2 being negligible, it equals Ks. Okay? So Km is called the Michaelis constant. Okay? And or I should say the Michaelis-Menten constant to be more thorough, and it introduces this whole idea of Michaelis-Menten equilibrium. Okay, and we are going to be talking a lot about it. I believe, where's the graph? Oh, the graph is a little later. Yes, right? No, it isn't. Okay, there was a graph here, and I don't know where it went. That's okay. I can draw a new one. Okay. So, which of the following is false regarding Michaelis-Menten enzymes? And okay. So, and we're going to select all that apply because there will be a few of these. At a low substrate concentration, enzymes follow first order kinetics. At saturating substrate conditions, the enzymes follow zero order kinetics. Enzymes consist of multiple binding sites and catalytic sites. Enzymes display hyperbolic curves. Okay, so let's just talk about Michaelis-Menten kinetics at first before we get into this. So the general graph that we see is a graph of substrate concentration versus reaction rate. Reaction rate, okay? So what happens is if I have a fixed amount of enzyme, so let's say for the sake of convenience, 1 molar of enzyme, okay? Then maybe when I have just a tiny bit of substrate, well, very little reaction is going to happen. And then maybe I get a little bit more substrate and a little bit more reaction happens, and so on and so on and so on. But once I reach maybe 1 molar of substrate, or we'll go a little bit larger because we're going to assume that not every substrate is going to bind to an enzyme very quickly. So maybe we'll say about 1.5 molars of substrate. Well, most of my enzymes are bound most of the time. And so getting up to 2 molar, or 3 molar, or 4 molar, and so on and so forth, kind of doesn't affect as much. Okay, and I realize that some of those have kind of gone negative. That was by mistake. It should have leveled off. Okay, something like that. And so the curve we get from Michaelis-Menten kinetics looks like this. Okay, so a couple of points that we need to make here. First, at low substrate concentration, the enzymes follow first order kinetics. So just changing the color here, if we draw a line kind of like that, that's pretty first order, yeah. And then at saturating substrate conditions, so to the right of this curve, it follows order kinetics. That's also the case, okay? And that overall makes this a hyperbolic curve, okay? But one of the most important details about Michaelis-Menten enzymes is that they cannot have multiple binding and catalytic sites, okay? And the reason behind that is because they're the relatively simple reactions. And so because the multiple binding sites and multiple catalytic sites would make this more complex, we're not a part of Michaelis-Menten kinetics because it describes general kinetics, okay? And so what these Michaelis-Menten, and actually it's Briggs-Haldane who came up with an equation using the idea that Michaelis-Menten came up with steady state. We have this new equation, or we came up with this new equation called Michaelis-Menten equation. And that's V0 equals Vmax times substrate concentration over Km plus substrate concentration. Okay, so we have two V's here. So let's talk about those V's. So Vmax is basically, if I can find my mouse at any point, there it is. Okay, Vmax is kind of that saturating threshold, at which point adding a ton more substrate doesn't really do anything. Vmax, okay, just doesn't help. All right, so we're going to go ahead and do a couple of examples that help us get into the using of this formula a little bit better. Okay, so a newly discovered enzyme was found to follow Michaelis-Menten kinetics. Further analysis produced the following equilibrium constants in K1, K-1, K2. So at what concentration will the initial velocity, or V0, equal 1/2 of Vmax? Okay, so what S will this be this? So what I'm going to go ahead and do is I'm going to say, okay, V0 equals 1/2 Vmax. I'm going to go ahead and substitute that into our Michaelis-Menten equation. So 1/2 Vmax, or V0, equals Vmax times substrate times Km plus substrate. Okay, well I can divide Vmax from both sides and just get rid of it. So now I get 1/2 equals, let me just slide over, equals my substrate concentration over Km plus my substrate concentration. So when we cross multiply, we get that 2S equals Km plus S. In other words, Km is equal to our substrate concentration. So what this tells us is, and this is the first relationship we need to bear in mind, the definition of Km is, let's see if I can approximate this. So if that's here, then so this is about 1/2 Vmax. The concentration at which the rate is half of the maximum reaction rate is defined as Km, okay? And that's how we get to that number. Now we have to actually find Km, and that's where these numbers are relevant. So Km, as we know, is, there it is, K-1, so 4.5 times 10 to the 5th, plus K2, 3.7 times 10 to the 2nd, over K1, which is 6.5 times 10 to the 8th. So, and I don't know that I need to explain this, but just in case I will, the orders of magnitude get confusing. Be careful. That's as much as I'll say, just because I don't want to waste time talking about that. But very briefly, this is a great example, by the way, of why we need to be mindful of, excuse me, of the orders of magnitude, because the number that we get out of this is 6.93 times 10 to the negative 4th, or approximately, I should say, 6.93 times 10 to the negative 4th. And that makes sense, but as we'll see in this next question, actually, let's do this question first. From the previous enzyme kinetics, which of the following is true? So the first, A and B are steady state or rapid equilibrium. We know that C is wrong because we're not talking about allosteric modulation. We know that D is wrong because it doesn't only follow first order kinetics. We know that because it's a Michaelis-Menten enzyme, it can't. KCAT is the rate limiting step in product formation. Okay, let's talk about, okay, I should reword that. So let's see which of the A and B are true. So we need to know steady state or rapid equilibrium. So as we talked about in problem 5, when Km equals Ks, it's rapid. When Km does not equal Ks, it's steady state. So let's calculate Ks and see what we get. So Ks equals K-1 over K1. And so that's going to be 4.5 times 10 to the 5th over 6.5 times 10 to the 8th. And from that, we get 6.92 times 10 to the negative 4th. So when we compare this number and this number, I'm willing to call those about the same. Yes, they're slightly different. They're pretty much the same. And so we know now that Km approximately equals S. And in that case, we have rapid equilibrium, as we talked about in number 5. Rapid equilibrium. Okay? Does it make sense how we got there from the math? Or rather, I should say, are there any questions about the math? If there are any questions, go ahead and type them in the chat. I don't hear any, so I'm going to just move on to number 9. So now we have another Michaelis-Menten enzyme that's been discovered, and we get those rate constants. So which of the following is true? So for this one, while we could do the math for them, I think that doing this a little bit more conceptually is more valuable. So, also I should mention, yes, E is technically true, and it is in fact true, but this question was more geared toward A and B. It's just one of those that I like to keep in to make sure that people are paying attention. Forgot to add it though. Okay, so K1, K-1, K2. So basically, our definition is if K-1 is significantly greater than K2, we have rapid. And if they're around the same order of magnitude, we have steady state. So K1 is massive right off the bat. K-1 is tiny, K2 is tiny. But they're both 10 to the third. So to me, that would indicate that we have steady state. Steady state, okay? And we can do the math to verify it, but I'm going to go ahead and say that the answer to this one is A. All right? Okay. So this is the next few questions are just getting used to using the Michaelis-Menten equation and finding different values from it. So these are going to go a little bit quickly, okay? For an enzyme that obeys Michaelis-Menten kinetics, what will be the initial velocity if the substrate concentration equals 3.5 km? Okay, so once again, we're going to write the formula. If I can find, there's my mass. Okay, V0 equals Vmax times the substrate concentration times Km plus the substrate concentration. And I'm going to go ahead and plug those numbers in. So Vmax times 3.5 km. And then on the bottom is going to be Km plus 3.5 km. We can clean up the bottom to basically just be 4.5 km. And then Km's cancel. Okay. Are we okay with that? Yes, no, maybe. Yes, okay, awesome. So now we get 3.5 Vmax over 4.5, okay? So 3.5 over 4.5, I think I might have done something wrong. Did I skip a step? Sorry, I just want to make sure, because I know that I did this problem before and got an answer. Okay. I believe I might have written this question down wrong. That's okay. We'll just and then we'll ignore the answer choices. Okay, so if it's 3.5 Vmax over 4.5 Vmax is equal to V0, I don't know how to do that in my head, so I'm just going to double them both, and we get 7/9 Vmax equals V0. So I apologize, I must have written something down wrong on the left. On the multiple choice, just ignore those. Okay, so yeah, so that's one of the ways we can use the Michaelis-Menten equation. Here's another. Okay, for an enzyme with Michaelis-Menten kinetics that has this V at this substrate concentration, what's the Vmax? So, and I'm just going to go ahead and plug those in. So I have 50 equals Vmax times 0.5 km over m plus 0.5 km. So now I'm just going to clean up the bottom and cancel the km. So that's going to be 1.5 km's cancel. So it's going to be 1/2 Vmax on the top over 1.5 equals 50. Multiplied by 1.5 to get to 75 equals 1/2 Vmax. Vmax ends up being 150. Okay. This is one of those situations where I didn't include units, or I kept all the units the same, I should say. Just being mindful of our units should be very important. Okay. Okay. So now we need to zoom out. So this is kind of so we've covered Michaelis-Menten kinetics quite a lot. Now we need to talk about Kcat over Km. So Kcat, like we talked about before, is about equal to K2. Okay, and I'm going to go ahead and write that on this side. We haven't really talked about what Km means. We've called it this Michaelis constant. We've called it, 1/2, or it's the concentration when 1/2 Vmax is a thing, but we don't really talk about what it is. Okay, and that's why I want to take a moment to do that. So Km, and I'm going to go back to its equation, K-1 plus K2 over K1. So K1 like we said earlier, is formation of the enzyme substrate complex, and K2, or I should say this top stuff, K negative 1 and K2, is the degradation, the breakdown, I'll stick to breakdown since that's the term that's used in a lot of your PowerPoints, breakdown of EX. So what it's telling us is basically the affinity of the enzyme for the substrate, okay? What that means is if Km is high, a lot of ES is going to be broken down and not a lot will be formed, okay? So the higher Km is, the lower enzyme affinity is. Affinity, okay? And the opposite is true. So in other words, Km has an inverse relationship. Inverse relationship. We're just going to try that again. Relation with affinity. Okay. So let's look at this graph, or this table, excuse me. And I got this table directly from Dr. Maloney's slides. I believe Dr. Gava has either this one or one very similar. There's another column that I excluded. So the lower K, the stronger the binding affinity for the enzyme for the substrate. Exactly right. That's a perfect description. So I want to look at carbonic anhydrase. Okay, so carbonic anhydrase can have two substrates. Okay, and I want to point out that these substrates are very, very similar. And in fact, if we know what carbonic anhydrase does, it catalyzes the CO2 plus H2O goes to bicarb and H plus. It has a substrate for the forward reaction, and it has a substrate for the reverse reaction. Okay. Now, there's Kcats. We can talk about Kcats in a bit. Let's look at the Kms. Okay. So according to Km, for which of carbonic anhydrase's substrates does it have a higher affinity? For CO2 or for bicarbonate? CO2, exactly right. So in my head, this is telling me that, okay, so that means that CO2 is more likely to bind to carbonic anhydrase. Depending on the rates, CO2 could very easily be like the forward reaction could be predominant just because higher affinity, possibly higher Kcat. And in this case, it is a higher Kcat. So to me, that indicates this forward reaction is going to be more likely than the reverse reaction, okay? And in fact, that's where this idea of Kcat over Km comes from. So like we said earlier, Kcat is turnover, right? It's the rate at which you form product, roughly, again, we're ignoring K negative 2. Km is the affinity for the enzyme. So if we go all the way back up to this equation, Km is the likelihood that you're going to get to an enzyme substrate complex. Kcat is the likelihood that an enzyme substrate complex will turn into product. Okay, so altogether, this is what's called the catalytic efficiency of an enzyme. Okay, right, and so a couple more practice questions for this that we're going to go into. So yeah, and then yeah, I'll explain the last topic later. So which of the following values is used to report enzymatic efficiency? Enzymatic efficiency is the same as catalytic efficiency. There's probably a dozen names for it that I don't know. There's my mouse. So yes, it is Kcat over Km like we talked about. Which of the following is used to report enzymatic affinity? And that's Km. Okay. The enzyme fumarase binds tighter or is more sensitive to which substrate? Sorry, let me reread that. The enzyme fumarase binds tighter to or is more sensitive to which substrate? So fumarase has two substrates, fumarate and malate. Okay, so when it says binds tighter to, is it talking about Kcat? Is it talking about Km? Or is it talking about Kcat over Km? What do you guys think? Km, yeah, exactly right. So we can compare fumarase's sensitivity to, as this question calls it, it's two substrates based on just their Km values. Okay, so which is it going to bind tighter to? What do you guys think? The higher KCAT, or I'm sorry, higher Km or the lower Km? The lower, exactly right. So the answer to this one should be malate, because the Km for malate is lower. Oh wait, I'm sorry. I'm bad at scientific notation. Please excuse me. Fumarate. Fumarate, because the Km for fumarate is lower, and because of that, it is it's more able to. It's got a higher affinity for it. Excuse me. Fumarate. Okay, and we can ignore C and D because it doesn't even bind to those. It has a very low affinity. Okay, what is the catalytic efficiency of carbonic anhydrase for both of its substrates, and what is the preferred substrate for the enzyme? Okay, so the preferred substrate, like we talked about earlier, is going to be the one with the lower Km. So it's going to be CO2. Okay, all right. The catalytic efficiency can be different though. Okay, catalytic efficiency is that kcat over Km, so let's go ahead and do that. So for CO2, it's 1 times 10 to the 6th over 0.012. And for HCO3 minus, it's, I believe it was 4 times 10 to the 5th, but let me double check, 4 times 10 to the 5th, good, okay. 4 times 10 to the 5th over 0.026, 0.026, we're just gonna ignore the first part. There, okay. So let's plug that into our calculator. And for CO2, we get the scientific notation that is 8.3 times 10 to the 7th. And for the other, we get 1.5 times 10 to the 7th. So the numbers we're trying to calculate, oh, that's the next question. Great job. You beat me to it. So the numbers are relatively close to each other, but it's very clear that CO2 is just such a better substrate for carbonic anhydrase. And that tells us a lot, right? Because remember, looking back at this, these two are in equilibrium with each other, CO2 and bicarbonate. So because we know that CO2 binds better, because we know that CO2 turns over better, like it synthesizes more quickly, we can conclude that CO2 is a much better enzyme, or I'm sorry, is a much better substrate for this enzyme than HCO3 minus. And that tells us that in this reaction between the two, the forward reaction is going to be the more predominant reaction, okay? So the next question, for which of its substrates is carbonic anhydrase a perfect enzyme? So perfect enzymes are really, really, really efficient enzymes, basically. And we call them perfect enzymes because it's kind of separating them out from every other enzyme and saying that it's exceptionally good for its substrate. And as was mentioned in the chat, that threshold is about 10 to the 8th, okay? 10 to the 8th, kcat over km. And the reason there's an upper limit, and actually, I'm going to turn this over to you guys. Why is there an upper limit? No? Okay, I guess I'll say it. It's the rate of diffusion. It just, it can't get any faster. And so because of that, you can never have an enzyme, or I should say, in real life, you'll never have an enzyme efficiency that's somewhere around like 10 to the 10th, 10 to the 11th. And it has been used on exams to trick a few students, by the way. Just be mindful, 10 to the 8th, 10 to the 9th is the only correct answer. So for carbonic anhydrase, 10 to the 7th, 10 to the 7th, it's neither, okay? I'll grant, did I spell neither wrong? I think I spelled it right, okay. I'll grant It's really close for CO2, but not quite. Okay, so that's pretty much it for the basic kinetic stuff. Okay, next we're going to get into my personal favorite section, and that's enzyme inhibitors. Okay, do you guys have any questions at all before we start that? Anything? Can you explain again about perfect enzymes, about efficiency? Can you clarify? Why the preferred substrate? Sure. So the preferred substrate, so the idea of the preferred substrate is for which substrate is carbonic anhydrase more efficient, right? And we can do this in two different ways. So the more complete way is to look at catalytic efficiency as the number. The way that I personally like to do it is I just look at these two, and I like just based on these two, we know that CO2 has a higher K-cap and has a lower Km, so it's got a higher affinity and a higher turnover. Okay, it's going to have a higher catalytic efficiency just from that. But in order to find the actual numbers, because it can't be a lot closer than this, we need to find the, and I'm sorry, I probably should have included the formula here. We use K-cat over Km to find the catalytic efficiency of the enzyme for each substrate. The preferred substrate is going to have the greater K-cat over Km. Okay? Okay, awesome. And just want to make sure, any other questions? Michaelis-Menten manipulating this equation. What are these called? Classes of enzymes, anything. Okay. All right, then we get to go to the fun stuff. Okay, so explain a Lineweaver-Burke plot with respect to the Michaelis-Menten equation, and then we're going to start doing inhibitors. So I'm not sure exactly where your professors have left off, simply because I know that they both are at slightly different places, and so I might be working ahead just a little bit. I might be a little bit behind. I'm going to focus a lot on the conceptual today, and next week we'll do some practice problems for it, just because I want to make sure that we're not memorizing, because this is a unit that a lot of people hate because it's all memorization, but it's really a lot more conceptual than people think, okay? So the Lineweaver-Burke plot is very similar to the Van Hoff plot we talked about in the first unit. It's a reciprocal, so we're going to take the reciprocal of both sides, so 1 over V0 is equal to Km plus S over Vmax times S. There we go. And then we're going to go ahead, since now the addition is on the numerator, we can separate it out into Km over Vmax times S plus S over Vmax times S, okay? Oh, I forgot to close that bracket. Okay, so now, I don't know if I need to explain this, the S's cancel. And on the other term, the Km over Vmax times S, we do the same thing as we did with the Van Hoff plot. We're going to write the S separately. Okay, so the overall equation is going to be 1 over V0 equals Km over Vmax times 1 over substrate concentration plus 1 over Vmax. Okay, and so a couple of important points. This also follows y equals mx plus b. You're almost certainly going to have to graph this for your problem set. Okay, so let's talk about some of the important things that we get from this. So the first is the slope. Slope equals Km over Vmax. Okay, the y-intercept is equal to 1 over Vmax. And then the x-intercept, and this one I'm going to do some work on above just because I, excuse me, I want to make sure that I show you guys where that comes from in the formula. So for the x-intercept, we set the y equal to 0 equals Km over Vmax times 1 over S. And then I'm going to go ahead and plus 1 over Vmax. Subtract this to the other side. So negative 1 over Vmax. On the left, we multiply both sides by Vmax to cancel those out. So you're going to get negative 1 equals Km over substrate concentration. We multiply by substrate we divide by Km. And so we get for the X-intercept, 1 over substrate concentration will equal 1 over Km. Okay, that's something that a lot of students don't get where it comes from, but it's mostly just algebraic manipulation. X-intercept equals negative 1 over Km. So generally speaking, I guess I'll do it over here. The graph for the Lineweaver-Burke plot will look something like that, okay? With your X being your substrate concentration and your Y being your V or your rate, okay? So I know that in this example, this is my negative 1 over Km. That is my 1 over Vmax. And finally, the slope of that line is, like we said, Km over Vmax. Okay. So now that we've explained this, we can get into inhibitors. Okay. So every inhibitor, and I want to zoom in a little bit more so we can talk about this in a lot more depth. So every inhibitor binds, before I do that, does anyone have any questions for ask? Okay, awesome. So every inhibitor has a certain part of this reaction that it binds to, okay? So competitive inhibitors bind specifically to the enzyme, okay? And the way that I will draw that is here, and I'm going to go ahead and put in an I for EI. So now what we see is our enzyme can form an enzyme substrate complex or an enzyme inhibitor complex, okay? And I want to think about this going all the way back to Gen Chem 2 with regard to Le Chatelier's principle. And I know a lot of you guys are going to say, gross, I hate it, but it's a really easy way to understand what's happening here. So, and all of this is going to be in reference to this equation. Yes, the product part is important, but it doesn't really change anything for the purposes of the equilibrium. So for this yellow equation, what is happening to my enzyme concentration? My inhibitor is binding to some enzyme, right? So when my inhibitor binds to some enzyme, it decreases the enzyme concentration, right? Decreases enzyme concentration. Okay, are we okay with that? Yes, okay, awesome. So if it decreases my enzyme concentration, what does it do to my Km? My Km, just a quick reminder, is the affinity of my enzyme for my substrate, okay? Actually, we're gonna pause before we get into this. Your Km and your Vmax are almost intrinsic values. Your Km specifically is really an intrinsic value of the enzyme. So when I say how does Km change or anything like that, what I'm really saying is how does Km appear to change, okay? Because Km is a constant, it doesn't actually change, but what we get is something called a Km apparent. And the Km apparent, exactly like you said, decreases, okay? So I'm gonna refer to Km apparent as just Km, but please note your Km is a fixed value. It's just, it appears to change. Does that make sense? I hope it does. Okay, awesome. So Km decreases. What about Vmax? Okay, and this is a pretty interesting question. increases because the affinity decreases. Thank you for pointing that out. I said that backwards. Okay. Will it increase for Vmax? It wouldn't increase for Vmax. So I want to go to, sorry, I am not the best with those. So this was our generic Michaelis-Menten graph, okay? So when I have low substrate concentrations, yes, Km does increase. Thank you, I apologize. So when I have low substrate concentrations, well, my enzyme substrate complex is going to be binding a lot. And in fact, it's going to keep binding. But what if I have a substrate concentration that's like 10 times my enzyme concentration and 10 times my inhibitor concentration? What if I have a substrate concentration that's 100 times, that's 1,000 times, and so on and so forth? Exactly, it'll overcome the inhibitor. And so while Km increases, or appears to increase, Vmax stays the same. Okay, it's unchanged simply because at some point your substrate concentration is able to overcome your inhibitor concentration, and that makes it about the same at some point. Okay, so let's talk about how the Lineweaver-Burke plot appears, because this is where we see most of this math. Okay, so there's our generic enzyme. So we said that when you have a competitive inhibitor, your Vmax stays the same. If Vmax stays the same, that means my y-intercept is the same. Oops, okay, I don't know why it did that. My y-intercept is the same. There we go. However, Km changes. And Km, as we discussed over here, if Km increases, our slope increases. And what happens to our X-intercept? I'll let you guys try this out. What's going to happen to our X-intercept as Km increases? As Km increases, it'll decrease, but it's a negative number, so it'll actually increase, right? It's one of those weird ones. Okay, yes, okay. So, and this is approximate, obviously. So I'm going to put our X-intercept here, because when our Km increases, it shifts, and then our slope is going to be somewhere like that. Okay? So this is a sign of a competitive inhibitor. If I gave you this graph on an exam, for example, and I said, this is the enzyme substrate alone, this has enzyme substrate inhibitor. What kind of inhibitor is it? You can easily say competitive inhibitor, because the rest of them do not have the same Lineweaver-Burke plot because they change different things. Okay? Does that make sense? Are we happy with competitive inhibitors? Or I should say, does anyone have questions about competitive inhibitors? Okay, terrific. Uncompetitive. So again, we're going back to this formula. And you guys will see I love this formula because I think it's such an easy way to get this concept, excuse me, that a lot of people really ignore, okay? So competitive inhibitors bind only to the enzyme. Uncompetitive inhibitors bind only to the enzyme substrate complex, okay? So I'm going to do this with, again, putting an inhibitor in here. And so what we get is called an enzyme substrate inhibitor complex, okay? So there we go. So let's talk about this with respect to Km and to Vmax, okay? With respect to Km, how does this thing change? Any ideas? Okay. Decrease? Okay, so someone said decrease. So let's talk about it. So again, and I probably could have highlighted this earlier to make it a little easier. We're only referring to this yellow equation. Okay. So what I see is my enzyme substrate complex concentration is decreasing. per Le Chatelier's principle, my reaction is going to compensate by shifting to the right. When it shifts to the right, I form more enzyme substrate complex to compensate. In other words, my enzyme now has an increased affinity for the enzyme substrate complex. Or, as was mentioned, Km will in fact decrease. Okay? Does that make sense? Are we okay with that kind of explanation? Yes, okay, awesome. So Km decreases. What about Vmax? Okay, so Vmax is kind of weird in this case. So whereas before with competitive, adding more substrate is able to overcome the enzyme substrate complex. Now if you add more substrate, all you're going to do is form more ES, and then that's going to shift that equilibrium to make more ESI, right? So what we see here with Vmax, and I want to give you guys a chance to answer it, so I'm going to pause in just a moment, is Vmax is going to change. How does it change? Any ideas? Yeah, it'll decrease because, I mean, increasing Vmax would be like improving the reaction, but this is an inhibitor, so it can't do that. So Vmax actually decreases. And a really important note here is the two increase at the same rate, or I'm sorry, decrease. So they, like, if Km is 1/2, then Vmax is also 1/2, okay? So how does that affect, so yeah, I'm gonna turn it over to you guys. How does that affect our slope? How does it affect our, hang on, I saw something in the chat. Yeah, at the same rate. So how does that affect our slope? And how does that affect our X-intercept and Y-intercept? I guess I'll do the easy one. The Y-intercept is 1 over Vmax. When Vmax decreases, it will increase. The slope, exactly right, will stay the same. Slope equal. And the two lines will be paired. You're exactly right, because the -1 over Km, when you decrease Km, that increases the number overall, but it's negative, so it's also going to it's going to shift to the left. Okay. So what we're going to see here is, let's see if I can draw this well. That's our generic line without an enzyme. This is our line with an enzyme, and the slopes are about the same because the lines are about parallel. Okay. So this is a classic uncompetitive inhibitor. All right. Does that make sense? Are we okay with that idea? Okay, awesome. So now there's one more major type of enzyme, or I'm sorry, not enzyme, inhibitor, and they're called mixed inhibitors. However, we very, very, very rarely talk about mixed inhibitors. And the reason for that is because, as I think you guys might be able to guess, mixed inhibitors are mixed. They're somewhere in between competitive and uncompetitive. So they bind to both the enzyme and the enzyme substrate complex. Okay. However, within mixed inhibitors, there's a specific type called non-competitive. And these non-competitive inhibitors bind to both equally. Okay. So mixed inhibitors bind to both, which is relevant. But again, we're going to put inhibitor in here. EI, specifically non-competitive are the ones we talk about, and I'll explain why in just a moment. But yeah, so that's what we get. So again, I'm going to highlight this equation because this is all we care about for now. Okay, so how does this affect Km and how does this affect Vmax? And one thing I'm going to emphasize is, once again, it has the inhibitor has an equal affinity for both. Exactly. Km is going to stay the same. Okay? And the reason is both enzyme and enzyme substrate complex will decrease, but they'll decrease at about the same rate because the affinity is about the same. And so it really doesn't change much. Unchanged. Okay? What about Vmax? What do you guys think? It'll decrease, exactly. So just like with uncompetitive, what we got was when this enzyme substrate complex is forced to make an enzyme substrate inhibitor complex, your Vmax decreased because more and more of it would go to that complex. The same rationale happens here. Okay, so how is that going to affect our line weaver Burke? Well, since Km is unchanged, I'm going to predict my X-intercept will stay the same. That's the easy one. All right, what about the others? Your y-intercept and your slope will decrease. However, your y-intercept is 1 over Vmax. So when Vmax decreases, this entire term increases. Increase. Okay. Does that make sense? Okay. Yes. Awesome. So let's draw that. So again, there's our just enzyme. So I know that my x-intercept will stay the same. So I'm going to go ahead and draw the line there. My slope will. I'm sorry, I did something wrong. Yes, I did. My slope will not decrease. I believe one of y'all said that and I got confused. My slope will increase. Yeah, so whoever said the right thing, I apologize when I was backwards because this decreases, so that increases. Increase. There we go. Sorry about that. And so we're going to get something that looks like that. Okay? So again, these are the classic signs on the Lineweaver-Burke plot that tell us that we have the various inhibitors that we have. And I'd like to go over them all for just one moment, kind of zoomed out so we can see everything. Okay, there we go. So with a competitive inhibitor, or actually before I do, does anyone have questions, like more specific questions they'd like to talk about? No, okay, so yes, I just want to make sure. Okay, so competitive inhibitors, because the enzyme has another thing it can bind to, its Km appears to increase while its Vmax stays the same because with enough substrate you can overcome the inhibitor binding, and so you get an increased slope with the same Vmax, right, and the same y-intercept. Okay, with uncompetitive inhibitors, because you're binding to the enzyme substrate inhibitor complex, you actually increase the affinity of the enzyme for the substrate, but in doing so decrease the Vmax, and because you're increasing the affinity, you decrease Km. So the slope stays about the same, and what you get is a slope that's shifted over to the left, or a line that's shifted over to the left. Finally, with specifically non-competitive inhibitors, Km stays the same, Vmax increases, or I'm sorry, Vmax decreases, which increases the y-intercept, and the slope overall increases as well, leading to a line with the same x-intercept but an increased slope. So now I'd like to very, very briefly talk about general mixed inhibitors. And this is, I should say, mixed but not non-competitive. So I'm going to put just the ones that aren't the non-competitive. So, and this is something I think can be very confusing, but it feels like you guys have a really good grasp over this, so I want to just introduce it. So, also have that same affinity, or they also have an affinity for both the enzyme and the enzyme substrate complex. However, they are not equal, okay? So whereas Km remained unchanged with non-competitive because it's about the same affinity for both, now Km will change. And the weird thing is we don't know how it will change, okay? Because it's somewhere in between the competitive and uncompetitive. So if it's got a higher affinity for the enzyme substrate complex, Km decreases. If it's got a higher affinity for the enzyme, Km increases. Okay? And that's why this gets confusing, because Km is going to change somehow. And we know Vmax is going to decrease. And so we know the slope is going to change. And so what we usually get from these is an increased Vmax with a different Km. So it can look something like that or something like that. Oh, that's actually a very bad drawing. Let me do it the other way. Something like that, actually. I'm trying not to draw them with the same slope, but it's kind of difficult. There we go, something like that. And so because of that, mixed inhibitors in general are not really easy to discuss for the purposes of this class. The fact that everything is going to change. Your X-intercept, Y-intercept, and slope will all change. We don't know by how much though, okay? And actually, it just occurred to me that this one would probably look like that instead. It would be a lot higher. So yeah, so mixed that aren't non-competitive are a thing. We don't talk about them just because it's too difficult for this class. The big three are the ones that you need to remember and understand at a really deep level, okay? So that's the end of this workshop in terms of the content. Very briefly, I'm going to tell you guys next week, we're going to be talking about a little bit of the calculations behind these, and then we're going to talk about the enzyme mechanisms and I think some of the models of like enzyme action. And this is one of the more memorization slash conceptual units where a lot of people will do one instead of the other. But I think that it's fairly good to understand it conceptually. Okay, so if you guys don't have any questions, I'm going to go ahead and stop the recording.